Hey kids, great news. Today we're going to learn how to evaluate this problem. Now, there's also some bad news. Had we been in class together, I would have given you this problem as a little bonus, and it actually would have been quite engaging to watch you guys try to work this out. But I'll still say that as we work through this lesson, this problem's going to pop up, and I'm going to encourage you to see if you can figure it out. We'll kind of just have the bonus right here in our hearts. Well, what is this problem? It's an integral. An integral. As you're going to find out, an integral is the same as the area under the curve. Yeah, the integral of a function is the area between the x-axis and the function. And we can actually have what's known as positive area. Now, positive area is going to be above the x-axis. And that's actually the way you've seen the problem so far. But we could actually have negative area, and that would be if we're below the x-axis. So, an integral. Now, as you can imagine, that problem that was on the previous screen indeed is an integral, but let's kind of figure out what all the notation is. Let me give you a general integral. So this is integral notation, and you would read this as the integral of f of x from a to b. This would be the integral of f of x from a to b. Why don't we do a little scratch off here, kind of like a lottery ticket, and we'll see what we win. If we scratch off this left-hand side, we find out that we win an integral sign. Yeah, that little squiggle is an integral sign, and it actually comes from the summation symbol. Although we're not going to talk about it in a lot of detail, the summation symbol, as you may remember from last year, is the sigma sign, and that stands for summation. And what we're actually doing is we're summing up an infinite amount of rectangles. Let's see what else we win here if we scratch off. Let's scratch off this green guy. This f of x actually gets a kind of a new name. It's called the integrand. But the good news is it's still the function. It's going to be the graph. It's going to be the graph that we find the area under, or as you now know, the area between the graph and the x-axis. What else do we have? I bet you could guess what a to b is. It's like we've already seen, but we have a name for a. We call it the lower limit. And we have a name for b, the upper limit. And generally, we call a and b the limits of integration. Now, we're not using the word limit like we did in the beginning of the year. It's not like it's an intended value, but it is the boundaries of our integral, the lower and upper limit. dx, what is that? Well, if we scratch it off, we find out that it's called the variable of integration. Now, I'm going to be honest with you, it's not going to mean much to you here for a while, but it needs to be there. And it needs to be there to make this problem two-dimensional. You see, one of the dimensions is the integrand, which is the y value of our function, kind of like the y value of our rectangle, right? And then the other dimension is the width of our rectangle. It's the change in x. And so what's really happening here is we have a y value times an x value. In other words, two dimensions, which is why this answer represents area. How about the bottom here? Well, it's as I said to you at the beginning. You see, you would read this entire problem as the integral of f from a to b. All right, so when you talk to your friends about it, you would say the integral of f from a to b. You ready to try a problem? It's not going to be that one that I showed you at the beginning. We're not ready for that yet. But it's a good little problem. It's the integral of 5 from -3 to 4. Now, if we were in class, I would ask you, what would you do? What would you guys, how would you begin this problem? And eventually, I hope you would say that you would graph it. You would graph what? Well, you would graph the integrand. You would graph the function. And the function is 5, which really represents a line that's equal to 5. It really represents the line y equals 5. And of course, if we graph y equals 5, we have some special points along the way, maybe the y-intercept, or maybe we just kind of note that the y value is 5. But once you get the limits of integration involved, you start to see the boundaries. You start to see the area that's between the graph and the x-axis. And so ultimately, this integral that we started with is really asking for the area of this rectangle. So what are some things that you're thinking when you think about the area of this rectangle? Are you thinking about its dimensions? Are you thinking about the overall length of this rectangle? Maybe, well, not maybe, but it's definitely equal to 7. And of course, the other dimension is equal to 5. And so when it all boils down, we end up doing nothing more than taking 5 times 7 to be 35. Now here's the cool thing. You just evaluated that integral, but you evaluated it using some basic geometry. All right, and that's our next step in this process of understanding area under a curve. You want to try one? Again, we're not together, but I really encourage you to pause the video now and see if you can evaluate the integral of -2 from 0 to 3. So how'd you do? You should be graphing or thinking about the graph. I would say you should be graphing the line y equals -2. Now, when you put the limits of integration on, you find out that we're actually only talking about this area. Looks like another rectangle, doesn't it? Are you thinking about the dimensions of the rectangle? You should have found the dimension to be a 3 by. Now, at this point, you could say by -2, or you could have said by 2. But the most important thing is that you understand that the answer to this, did you get it to be negative? The answer to this integral is -6. Do you see the area is under the x-axis? And remember what we said a couple slides ago? That's right, it's going to have to be negative area. Now, so far we've done 2 problems that you're going to say they're kind of basic, but they do have a pattern to them. In fact, they have a pattern that we could discover without the graph. If you just kind of look at the numbers, do you see the only 2 numbers that we really need in order to satisfy each of these problems? Do you see that it looks like that we only need the actual function, that constant value? And do you remember where this dimension came from? See how we can get it from our limits of integration? The dimension of 3, the dimension of 7. Well, we would discover that it's simply the subtraction of a and b. Now, what we have here is a little theorem, a little rule that works for the integral of any constant. And so the integral of a constant, now a constant's just a c value, is always going to equal that c value times b minus a. And of course, b minus a is just the dimension, the distance between the lower and upper limit. Now I want you to notice that we always subtracted b minus a, so it's always the top minus the bottom. Now, this little formula can be helpful. It can be helpful for problems that involve a constant. And again, just to get the idea here, what we're saying is that you don't need to make a graph in order to do the integral of a constant. If you recognize that this is just a constant, you can simply take that 6, that constant, and multiply it by b minus a, multiply it by 11 minus 4. And so this problem becomes some simple math, certainly just 6 times 7. Now, a little bit of a confession here. I prefer you to make a graph. In fact, most of the problems that we do are going to involve a graph. But if you notice that it's a constant, you can use our little formula. What if it's not a constant? What if it's more of like an equation? What if it's the integral of negative x over 3 plus 2 from negative 3 to 3? Now, this is a problem that we started with at the beginning of the lesson. And here's where I'm going to be honest with you that this is the next step in your process for you guys to think about this, for you to actually take a good quality 10 minutes and see if you can find the area of this integral. You're going to have to figure out what in the world the graph looks like. You're going to have to think about where the area is. And then once you see where the area is, you're going to have to do some good thinking to actually find that overall area. So you've got a decision to make. Some of you, you're like, yep, I'm going to pause this and I want to try this problem. And I'm going to say to you guys, great, that's exactly what you should be doing. But I know some of you are just going to keep the video rolling and you're going to kind of watch what happens. I can't stop you from doing that, but I can caution you because you're going to miss out on this next step of thinking that you really need to do on your own. All right? So are you person number 1? Push pause. Are you person number 2? You're going to keep the video rolling and you're going to miss out a little bit. All right, so how'd you do? Although I can't have a student put their answer up on the board and I don't have a way to check your answer right now, the first thing that you should have done is graphed it. Now, if you graphed it on a calculator, you saw the whole line, negative x over 3 plus 2. Once you graph it on your calculator, you have to start to find the actual space, the actual area that's between negative 3 and 3. Now, I prefer to take this and, of course, turn it into a sketch where we can start to kind of zoom in and mark this up a little bit more as we desire. So here's negative 3 to 3 that is now contained under our line. Just a little note here. Did you not let the x-intercept sort of fool you here? Although the x-intercept exists, it's actually not really, and it doesn't end up being part of our final region. So we're going to force ourselves just to focus in here. Looks like we kind of have a region that some people might call trapezoid, or that some people would say is a triangle and a rectangle. Now, this kind of method of dividing this region up is a good call. You guys will use this quite a bit in this chapter, and starting to understand some of the dimensions can be helpful. Now, those points insinuate a certain y value that would correspond with each x value. So knowing that the y value is 1, or knowing that the y value, what do we get here? That would be 3. So finding those y values is helpful. How about starting to think about the two shapes? Of course, we have a rectangle. This rectangle has a overall length of 6. That's kind of a number we've seen before, but now we're able to say that the y value, at least over here, the y value ends up being our dimension, our other dimension. And continuing, if you think about this triangle up here, it too has a base and a height. I hope that you would deduce that it has the same base. It still has a base of 6. But we can come up with the height of this triangle by thinking a little bit more about our 2y values. So, of course, we're going to have to fill in that difference with 2. So we're getting a little closer. We basically find ourselves finding the area of a rectangle. Maybe we can call that region 1. And that region 1 is just going to be a 6 by 1. Of course, again, that turns out to be 6. Then we have our other region. It's going to be the area of a triangle, which is 1/2 base times height. And, well, that also ends up being an area of 6. So it looks like we're going to end up with an overall area of 12. Now that does end up being the answer to our integral. I will share that it doesn't end up being the only method to get that answer. Again, if we were in class, there'd be some other techniques that some students would share. One of those techniques may have been that you did actually use the x-intercept. Students that use the x-intercept, which, what does that come out to be? Is that over there at 6? Students that use the x-intercept sometimes will be the same students that kind of see this answer as being a large triangle minus this extra space. And so maybe you were in the camp where you actually saw the ability to take a large triangle minus a smaller triangle, kind of like a whole minus the part. And I say to you that that's a fine method. I guess it would mean that we would have some different areas of these triangles. What do we get here? The base this time is more like a base of 9. I'm talking now about this big red triangle. So we end up with 1/2 of 27. And of course, we have to find the area of our little triangle. What kind of base do we have here? We have a base of 3, and it has a height of 1. So it looks like it's going to be 1/2 of 3, otherwise known as 3/2. So pretty cool. Just basically because it still works. I think we're going to end up here with 24/2, which of course is the same number as 12. So that's another strategy. And there could be some other ones out there that I've seen, but of course, without us being in class together, it's hard to show them all. The bottom line here is that we can start to find the area of any type of line. It doesn't have to just be a horizontal line by starting to think about dividing the shape up, whether it's going to be divided up into a rectangle and a triangle, or maybe 2 triangles with some subtraction. We're getting a little closer to understanding the integral. Now, the next time we're together, we'll continue to talk about integrals using some of these same strategies. And so I look forward to getting back together with you so that we can do that.